Welcome to our presentation on supercharging operations and analytics using Spring XD to support analysis, analytics, and operations. My name is Joseph Paulchell. I work for CapitalOne, where I am a master software engineer and a team lead.
My name is Jason Baumgartner. I'm a developer on Joe's team, working mostly with Spring XD. I'm the Spring XD lead developer on Joe's team.
Okay. So within CapitalOne, we have an internally developed Java framework that's based on, well, Java and Spring. And we use that internal framework that we call Chassis as the foundation for building a lot of our customer and consumer-facing applications, as well as some of our internal-facing applications. And within that framework team, one of the pieces of work that we've taken on is this idea of data streaming and data batching. And so we, Jason and I, form the core of that team that are looking at Spring XD and the integration of our chassis-based applications and using Spring XD to move data back into our various big data tools and sinks. So we look at Spring XD, look at the technology, where Pivotal is taking the technology, conduct proof of concepts, and try to do some innovation, as well as help application teams that are looking to use this technology to implement it in the best practice way. So first, I want to just tell you a little bit about who we are, where we come from. So we are from CapitalOne Financial, which is both a technology company and a bank. So as a leading diversified bank, we have billions of dollars in assets, loans, and deposits. We are a Fortune 500 company, currently ranked number 124 on the Fortune 500 list, with more than 65 million customer accounts and major operations in 15 cities, including the UK and Canada. We have around 46,000 highly talented associates working for the company, and a large number of those associates are in our technology division, right, working on developing software and technological solutions. And our goal with this use of technology is to try to harness that technology to delight our consumers and customers by enhancing, improving, and simplifying the banking experience. And hopefully everyone in here is a CapitalOne customer. Glad to hear it. So very briefly, some of the topics that we're going to cover in the next 80 minutes is we're going to basically very, very briefly set up what the business problem is and what we're here to talk to you about. Then we're going to talk about our journey at CapitalOne from the legacy solutions that we had and how we were trying to capture data and solve this analytics and operations problem, and how we implemented Spring XD and how we evolved with Spring XD in our solution for capturing data, providing it to different tools, and supporting the goals of the enterprise for doing complex event processing, dashboarding, reporting, and a number of other solutions. During the course of this talk, we're going to show you some Spring XD deployments, some stream definitions. We're going to show you some snippets of code from both our internal libraries, some other configuration, and we're going to talk about some of the interesting technical challenges that we had and where we've provided a solution. We're going to talk about like how we solve some of these problems. All right. The caveat here is, of course, that these technical implementations we've done, there's many different ways as software engineers to solve the problem. And we're just going to present to you what we did internally. But we're planning to gather information from this conference and evolve our solutions just like Pivotal is evolving Spring XD into its next generation. And then at the end, we'll show you some sample dashboards in a couple of different tools to show you like what we're doing with all this data. And then if we have some time at the end, we'll talk very briefly about how we're provisioning XD in the cloud. So I want to start out with just a couple of quotes that I think capture the essence of what we're trying to do and what we've noticed along the way. The first is gathering data is important, but it is crucial to be able to differentiate between data that's merely interesting and data that actually provides leverage. And this is key. It's easy to collect a lot of data. It's a little bit harder to figure out, of all that data, what data is useful. And so one of our things is to both enable the collection of a lot of data, but also to support that identification, triage, and use of that data to find interesting little insights that will help us improve that banking experience. The second quote I like because it's very indicative of what happens when we're working with large sets of data. And that's the alchemists in their search for gold discovered many things of greater value, which means when you're looking at this problem here, sometimes the path of the solution to that problem, you pick up some things along the way that you weren't intending to find. And then oftentimes you can find some very interesting value there along the way. So I'm going to tee this up with an example from within CapitalOne, one of the things that we noticed that kind of gets to those two quotes. All right, so our data scientists noticed an anomaly in the millions of customer logins that were being collected every day. And that the small number of logins were failing despite the consumer providing the correct credentials, right? That shouldn't happen. So they sent back to these various data repositories that we had, and they started combing through that data, and they noticed two distinct attributes for these customers that fell into this very small bucket. The first was that these customers were using a device we'd not seen before. They were using a brand new browser, a new mobile device, or what have you, and we had never seen them interacting with us using that device. And the second one was that they did not have multi-factor authentication challenge questions recorded in our system. And those two combinations of things really should have never happened. Should have been impossible for them to have valid authentication credentials without MFA questions. And just for those who don't know, MFA questions is when we will challenge you. Answer these questions so that we can be sure that you really are who you say you are. And then combing through all that data, what they found was that this was a case where, for some reason, customers are interacting with an agent, and in a part of that process, they were instructing the agent to reset their MFA questions. And then when they tried to log in and hit a situation where they had to be challenged, there were no challenge questions. And the existing logon code didn't accommodate that. So a little bit of gold we found along the way that resulted in an incredibly trivial code change that resulted in removing something that was a dissatisfier for a number of our customers. So our challenge was to find a way to harness those millions of customer interactions, the tens of millions of request responses and messages that we're providing, because every single one of them can be very interesting, because we never know what those interactions might find in terms of little tidbits of information along the way. Our goal then was to provide capabilities that would simplify the collection of that data, enable the delivery of that data where it was needed, when it was needed, to be able to scale it up quickly, avoid undue burden on the client applications to record that data, and to provide data in a standardized format. All right, so let's talk about our journey. Jason?
So, like Joe mentioned, we're on the internal CapitalOne framework chassis, and the framework itself is about 3 years old. Now, our first crack at getting application data out of the apps and into the system of record at the end looked exactly like that. We had a Java application running in a vendor container, writing to a local queue, and then we had a co-deployed application that would read from that queue and insert it into the RDBMS. Once it's in there, there were ETL jobs on the backside where they would extract that data in batches, nightly or hourly or whenever the cadence was, and then they would generate reports and dashboards. That worked. It worked at the size of the framework that we were at that time.
Yeah, so our framework made it very easy to collect data. So with this chassis framework, our internal framework, we packaged an easy solution that made it easy for these applications to use Spring annotations to decorate their code, to capture data about what was happening within their applications, and then move it out to that local queue and off to the database. All right. We then expanded upon that to allow them to use Spring expression language in those annotations to create a richer set of data capture. And then because that data capture and the consumption were decoupled from each other, those two things can kind of scale somewhat independently of each other. And then we implemented durable queues in certain cases to make sure that we didn't lose information that was relevant. So for example, if we were creating a durable audit trail of customer activity, for example, we extended an offer to this customer and they accepted that offer, we wanted to create a durable record that said that we did that thing on behalf of that customer at that time. All right? Now, if you looked at that architecture, you'll notice one thing. It kind of looks similar to what you've been hearing about with Spring Boot, right? Independent applications communicating via message bus. So here's an example of what those annotations looked like for us. At Audited at the class level basically said every attribute within that class was then going to be captured, handed off to one of our builders, and then turned into a message, put on that queue, and then consumed and written out to the database. The other thing we had was this annotation at audit. And basically what that would do is record the execution of that method. And it would take the execution of that method, the attributes of the method, the return of that method, package that all up, hand it off to a builder, and that builder would assemble the message, put it on the queue, and away it went to the database. Easy, right? However, as operations started to collect that data and they started to comb through it, they started to go, wow, this is a gold mine of really rich data, right? But they wanted to make sure that we were capturing lots and lots of data, and they were capturing the data that was most interesting and most useful to them. So they started making requests to enhance what was being captured and to capture specific types of value that weren't necessarily a part of what those method signatures were. And so we started to end up with code in the application tier that looked like this. Kind of much more complex audit statements using Spring expression language to determine, well, when the submit payment transaction occurred, we should be capturing the payment amount, the transfer account number, and some other parameters, return values, if exceptions occurred, throwing all those things into a builder and logging it off to the database. So now the method that was very simple became cluttered up with all of this expression language just to record the values. And so the application developers started to complain a little bit about how invasive the data capture mechanism was to what they cared about, which was writing a really fantastic application to service customers. So as we started to scale up this approach, some challenges started to emerge in the growth of this solution. We were gathering over 450 gigabytes of data a day just on the initial applications that were onboarding. Our central relational database quickly grew from 2 databases, one in each data center, to 10. And our ETL processes were running much, much longer so that we were missing SLAs on a continuous basis. In addition, the operations folks were saying, you know what, I don't want to wait until tomorrow at 7 or 8 or 11 a.m. to have my data. I want to see my data more frequently. So nightly batches became hourly batches, and hourly became every half hour. But the real goal was always deliver the data to me as you're recording it. Real time was the goal. Okay? And also it was hard to get the right data. We had some applications where they were just auditing everything, literally sent everything. That just created this flood of data where it became hard to sift through it and find the 10 needles we cared about in that enormous haystack. Or we had cases where they were logging a lot of data, but they weren't logging the data that the operations and analytics folks really needed, right? When a customer tried to submit a payment, was it successful? Was the customer told, we've got your payment, the payment has been recorded? In some cases, they had to sift through a whole bunch of API calls and traces just to try and figure out, well, did it work or not? Right? Which made it hard to triage and support and find customer issues. And of course, you saw the spell.
So the back-end databases were getting overloaded. They were missing ETLs. And as an incremental improvement, we introduced Splunk into the picture. We've still got applications writing to a local queue, but now we're forwarding that queue, and Splunk is reaching in and taking that data. Once it's in Splunk, you can make those dashboards, you can do analytics, and you're not stressing the back-end system of record with constant batches and requests for information. So that helped. That was an incremental improvement. Splunk was reaching into every single container, though, so that was a wheel and spoke model. But this helped. It was an incremental improvement.
Yeah, so now we've got that data in Splunk, which is great. We've got another avenue for folks to record it. But what that meant was that Splunk was reaching in, like we said, to every single one of these containers, right?
Mm-hmm. So Splunk helped, but once the data's in Splunk, we were on a 90-day limit. So the data's in there, it's in there for 90 days. If you wanted it in another store, you're still batching it from either Splunk or from the RDBMS. So, you know, there are only 2 avenues out of the application. It's Splunk or the RDBMS. And if you want it in a third, you're doing another batch. And then while Splunk is a great tool, it can't solve every problem. So what we really wanted was we wanted to send the data where it should go the first time. It should be simple.
All right, so as we started to think about those constraints, we also started to look at what was happening within the enterprise with what we were doing with big data tools. All right? So we had a large and growing investment in Hadoop. So currently we have 2 petabytes worth of storage in our Hadoop data lake, which is pretty significant. So 1 petabyte is 2 to the 50th bytes, or 1 million gigabytes. So we had 2 million gigabytes of storage, and we're just flooding that with all this data from all these consumer and customer touch points. All right? In addition, we identified Kafka as kind of a linchpin in our infrastructure, and that on the path to getting data in the Hadoop lakes, we wanted to land data in these Kafka topics so that other consumers could basically pull that data off, so that data scientists could get data out of those Kafka topics for their own reasons, or we could move data into other use cases on its path to the lake. In other words, we didn't want to wait for the data to land in the lake, get registered, ingested, map reduced, et cetera, before we could pull it out and make use of it. And so Kafka was identified as one of the solutions we wanted to implement for that. And then, of course, we mentioned operations. The ops and analytics folks came to us and were table pounding. Right? We absolutely want this data in real time. We want real-time feeds. And their goal was to create these things they call rolling window dashboards. They wanted to build dashboards that were constantly updating with real-time streams of data so that we had a rolling view of exactly what production looks like for all the things that we were measuring. And from that rolling window, we found that we could be more accurate in terms of predicting what we think is going to happen next, so that we could basically look at the heuristics and say, hey, you know what? We see this type of behavior, right? Complex event processing. And this type of behavior is typically predictive of this thing about to happen in the future, whatever that might be. Right? The other thing is that we're looking at a significant number of big data tools internally, right? And the laundry list of names is staggering, right? Pig, Mine, Voldemort, Druid, Drill, I mean, just about any name you can come up with. We have data scientists and data folks who are analyzing it, doing proof of concepts, advocates. I see a lot of people smiling. We're not the only people that have this, right? No. Right. All right. So how many people in the room have at least 5 big data tools? At least 10. Okay, we got all you guys beat. We have them all. We have Flume, we have Spark, we have, you name it, it's all in there. And so out of that, we're playing with a lot of this stuff. And we're trying to figure out which tools and which approaches are going to fit our particular needs the best. And then out of that, yeah, question?
Just wondering if you guys are using any time series databases.
Any time series databases? I don't think so. I don't think so. But our lab folks out in San Francisco, Chicago, New York might be, and I'm just not aware of it. Yeah. But if you name it, with possible exception of that one, we're probably playing with it. All right, so finally, we're getting on to like XD, right? So we needed a different answer. We needed a different solution, right? So what were the qualities that we wanted that solution to have? First and foremost, we wanted it to be open source software. And I'm sure everyone in here has that same desire. We wanted that solution aligned to our internal skill sets, which means we wanted it to be Java, and we preferred Spring, because our internal framework uses those. We wanted it to be easily able to receive messages from the applications in our inventory, which means we wanted to have support for what we were doing today, which is JMS or HTTP. We wanted it to be able to write to the syncs that were most relevant for what we were doing. HDFS, Kafka, Mongo, relational databases, file. We wanted support for asynchronous, synchronous processing. We wanted a solution that was modular, something that would support reuse and composition so that we could write components and make them available to other folks through our internal GitHub processes so that they could then build upon the work of others. And because within CapitalOne we do a lot of community-based development, we wanted to enable others to be able to see what people had done, contribute to it, and incrementally enhance it. We wanted the solution to be easily scalable, highly performant, and we wanted support for the cloud. So that's what we went shopping for. Now with Spring XD, and here I'm going to stop, like, how many folks have Spring XD internally? Okay, so we've got some people, great. Are you in production? A couple people, it's sort of, okay, so we got one definitive and a couple in production. Okay, we have some stuff in production as well in kind of what we call our associate beta, which is where our internal friendly group of associates are using the tool and banging on it in a production mode. And very soon we're going to have this in a more like stable production environment. But XD provided us the qualities that we were really looking for. It's open source, it's Java, it's Spring Boot, and it has a laundry list of sources and syncs out of the box. All right, HTTP, TCP, Kafka, JMS, Splunk, file, HDFS, and the other HDFS formats, Avro and Parquet. Additionally, Spring XD is easily scalable. You can add more Zookeeper, you can add more containers, so you can grow the cluster. And you can do that by just adding +1s and +2s. We can share it, which means that I can create an environment and I can have multiple different streams on there for multiple different applications, all co-resident in the same ecosystem. But I can do that in such a way that those streams are isolated by targeting certain, I'll call them workloads, to different containers. And we'll see later on examples of how we do some of that. I can freely interoperate between batch and real-time processing, which means I can get a file in and trigger a bunch of stream processes, or I can receive messages on stream and record them into files that are then picked up later by a batch process. It's module driven, but I can also take those modules and assemble them into composites. And it's, at least from what we've seen, it's very highly performant.
So streams and taps of streams were fundamental in Spring XD's appeal to us. If you recall from the first diagram we showed, we had application in the queue going to a single endpoint, or we were duplicating that data on a queue in the container and going to Splunk. And we wanted to write the message once, no duplicating, and then send it through to the endpoint that it belongs to the first time. And what a tap allows us to do is read that JMS queue, take that message, send it to the RDBMS like we've always been doing, but now we can tap it off to Mongo, we can tap it off to Splunk, we can create a custom processor that transforms this raw audit client data, and it transforms it into a format that our back-end data guys had requested. So we can take that formatted data, format it in stream, and put it where it needs to be. And we can also tap at any point before or after a processor. So it gives us flexibility in where we want our data to be, what we want it to look like, and even filtering and routing based on the contents of the messages themselves.
Yeah, so the solution made it very easy for us to kind of meet those initial needs, and also with taps to support what we call experiments in production, right? Because my main flow of data continues to move, we can just tap that data off and we can support kind of experiments on that 65 million customer account base in production, and we can observe those things and play them into other tools and other solutions without impeding the normal production process.
So we could take this production audit data and tap it off to ELK, say, Elasticsearch.
Yep. So you had a question?
I might have the answer, but I was just wondering what, give a concrete example of a composite module that you're talking about. I understand what it is, I'm trying to visually understand what
Sure. So Spring XD supports what's called a composite, and that's where you can take any set of modules that make up a stream definition. So if your stream is, let's say, a Rabbit source, and then you're doing a custom processor that, let's say, is scanning the incoming payload and looking for the word error, let's say. And then it hands it off to another thing, which then trims out all of the noise in that error message, and then it sends it off to Splunk or an alerting dashboard that's going to operate on that. You can take that processor, formatter, Splunk, package them all up as a composite module, and then deploy your composite module. So now future stream definitions could be Rabbit in that new composite module. And that way, that composite module becomes sort of a Uber component that's all deployed together.
And
it's your composite transformer.
Yeah.
And it will all go to the same container, so you get a speed bonus, but you sacrifice the ability to tap because they're all doing local transport within the memory.
Mm-hmm.
So this is what our architecture looks like now. If you remember from the first slide, we had the app, the queue, and then a second app that was co-deployed in that container. That's gone because Spring XD is now streaming that data from the JMS queue. There's no more forwarding queue. That's gone because the stream is reading it once, then it's transforming it, it's tapping it to Mongo, it's tapping it to Splunk, and it's sending it to the RDBMS, the system of record, as usual. Now, the application teams, they have no idea this happened. They don't have to change their application at all. Actually, all they have to do is undeploy that co-located audit service app and hit delete on the forwarding queue. So they don't have to do a single code change. They don't have to change any properties. They don't have to redeploy anything. It also gets rid of the wheel and spoke model where Splunk was reaching into the containers themselves. So we've simplified our architecture.
Yeah, so go ahead.
Yeah, so then let's say somebody wants to add a property to the expression. You know that becomes really funky.
Mm-hmm. You mean the spell? You mean the spell expression on the audit annotations? Yeah, so if someone needed to change the spell expression, then that resulted in a code change, a QA verification cycle, a redeployment of the application. And we're actually going to talk in about 5 or 10 more slides about what we did on the client side. So that's a great forward-looking question. Fantastic. Yes, sir?
Are you still using Kafka in here?
We are, and we're getting to that.
We'll get to that.
So when Jason said this is our architecture now, actually this is an evolutionary step. This is we evolved to this, but that wasn't good enough.
Yep. So this was the next step. So it was basic, then Splunk. Now we've improved a little bit more, and we'll get better.
Yes, sir.
What's the migration process like? It seems like you can only really take advantage of a tab if everybody else is already participating in the next ecosystem. Like, how do you do it if you've already got an established process that's going over CJOS, point A to point B? How do you tap out?
Okay. So the question was, what was the migration process if all applications are not on XD?
Right.
Okay. Yeah, so if you're not using XD to move the data through, obviously we can't tap that data, right? So in those cases, let's say we had application A that was delivering their data to relational databases, it ETL'd out to Teradata, for example. All right, so we'd have to find a way to take that data and marry it up with the data flowing in another way. All right, but once application's on board and their data is moving through, then it becomes really easy to tap it and move it into Kafka topics or move it to a central Mongo database that had a filter in front of it that said, hey, the only data that's going into this Mongo database is customer logon activity, right? As an example, yeah.
Or you just broadcast it to the topic.
Yeah.
Any interested party can listen to that.
Yes, yes. And that's one of the things you get with Kafka, although we're going to talk about a Kafka challenge in a moment. Okay. All right, so yeah, architecture slimmed down. So this is the next evolutionary step.
So all of that streaming and tapping and splitting of the data, that's all done with these three stream definitions. The one on the top, you'll see that it's a JMS source. You plug in the broker configuration, and that's the address of the application with the queue itself. Then you put in the name of the queue that you want to read from. We've got our custom audit processor in there, and all that does is it transforms the raw audit JSON into a format that's preferred by our data guys. And then you'll see the next line, we're tapping that stream, we're sending it off to Splunk, which eliminates the need for Splunk to jump into the container itself, and then we're tapping it once more to Mongo. Again, the applications aren't aware of this. All they have to do is undeploy that original audit service application that was co-located in the container. Their application still writes to the same queue, it's just now SpringXD's reaching in and streaming from there.
Yeah. Now in this example, obviously we've stripped out a lot of the details around the processing that's occurring along the way, just to kind of illustrate the process. But it's very, very simple using the stream definition mechanics to create these three flows of data. So I've got this enormous stream of millions of customer transactions, right, heading to the system of record, which right now is a relational database, but we're going to get to like the Kafka implementation. But then I could tap that data off and send subsets of it to different places for different reasons. George, did you have a question?
For that processor that's massaging data or how the folks want to see, is that written fully or Java?
Yeah, so the question was the custom processor in our processing chain, and what language is it written in?
It's just Java, yeah, it's a jar.
Yep.
So this is a quick visualization of the path the data itself takes throughout a SpringXD stream. So we've got a stream that's got three components, HTTP, the audit processor, and Mongo. And then for simplicity's sake, we'll have 3 XD containers. The default behavior on a stream deployment is to deploy those modules round robin, and then each hop between those containers goes on to the message bus. And you'll see that those two queues on the message bus, they're automatically created and automatically namespaced. And when you're tapping, you're actually reading from one of those queues. So you're duplicating from one of those queues. You can tap at any point where you go onto the message bus. And with a composite module and you put them all on a container, you get some speed, but since it's not going on to the message bus, you lose the ability to tap. So that's a trade-off.
Yeah, so those taps essentially create a fan-out queue, which is then consumed, sort of a pub-sub mechanism, by any tap that's then hitting on this stream. Mm-hmm. Right, so this kind of shows you the way the data is flowing through. And you can note, by the way, XD bus is the prefix, but you can configure that in the servers.yml or one of the other deployment files.
Yeah. So you could tap before the data is processed or after. Anytime it's on the bus, you can tap.
Right, now, there was a question earlier about, well, what's the deal with a composite? So if we had taken like the audit and the Mongo and built that into a composite, then that module would have been deployed as a whole to just one component, and you would have had one less messaging queue involved in the movement of the data.
So here's just a quick view of what those queues look like on the message bus from the RabbitMQ console view. You'll see there's the first step. The second line there, that's it's postfixed with DLQ, dead letter queue. Because we're dealing with audit data in our use case, we don't want to lose that. Let's say there's a network issue, there's some sort of partition, and the sync is unreachable. The messages will build up in the dead letter queue, and then we've got a process for resubmitting those messages in a retry process so that we can get that data through. And then that very long one at the bottom there, that's what a tap queue looks like in the actual RabbitMQ console.
All right. And so with the retry logic, this is supplemental to what XD already provides with retries. So that the syncs can be configured for a certain number of retries and a certain wait period between each retry. And so like the default might be 1,000 milliseconds, and then there's a multiplier like 2. So it's 1,000 milliseconds, then 2,000 milliseconds, then 4,000 milliseconds. And so it'll try usually 3 times before it throws it to the DLQ. And then if you've configured your RabbitMQ, those messages on the DLQ can get then reprocessed through, which is what you're kind of seeing here. So there's a lot of different configuration options that are a part of what you get with Rabbit that's supplemental to what XD has. So if you're using XD with Rabbit Transport, which is what we're doing, you have a lot of capability around configuring each stream and each module and the way that it moves those messages and how it deals with failures. All right, so here, one of the things we want to highlight is something that was particular to our organization around Mongo. So our architects had specified that they wanted Mongo to run in what are called replica sets. And so we had 3 Mongo instances with the potential for the master to rotate between the replicas in the replica set. And that meant that if they're under certain conditions, those writes to Mongo might fail. I saw a head down the back. Someone's going, yep. All right, so we had to make a minor change to the out-of-the-box Mongo sync. You want to talk about it?
Sure. So the out-of-the-box Mongo sync, it relies on the Spring Data MongoDB jar. And that jar already had the ability to write to the replica set. It already had the XML tags. So all we had to do was edit the XML configuration for the Spring XD Mongo sync. And we just dropped in that tag right there. It's just writing to a replica set, comma-separated list of the host and port. So it was pretty simple.
All right. Now, if your Mongo replica set requires authentication, then the change was was a little more involved. So in this case, what we did was we set up in a properties file a MongoDB kind of URL that specified the user, the password, and then the host and port of each item in the replica set. And then we built within the Spring configuration some beans, the Mongo URI, which then used that external property, which allowed us to change that by environment, so dev versus QA versus production. And then when we basically create the Mongo itself, it's using that Mongo URI, which will then handle the authentication. All right, so that way you got user password. Yeah, so I got head nods up there. So, yeah. So this is what we had to do with writing to Mongo with a replica set. So if your environment, they want to use Mongo with replica sets, here's what you need to do.
Question?
I do. Remember during our XD class, we touched a little bit on the security part of accessing the database. If you guys have so much time, would you touch on how you solve the problem of not putting quick key passwords and probably files?
Sure. Yeah, the question was, within Spring XD, some of the data connect strings require, obviously, IDs and passwords. Same thing, by the way, with the HTTPS properties file. So there's a clear text password, which is the key to the key store that's used for storing your SSL certs for inbound HTTPS. And those properties files, the passwords are in clear text. Right? I think, is it also in the stream definitions?
It's in the stream definition.
As well.
Yep.
So the question was, how did you deal with that? And so we said, okay, if we have some time, we'll come back and talk to you about the things that we're doing in that respect. Yes?
The original architecture diagram did not have MongoDB in the picture, and I noticed that evolution introduced it. Could you answer why it was brought in the picture?
Yeah, so the question was, one of the diagrams we showed didn't have Mongo, but then we've just talked about Mongo replica sets. So when and why did we introduce Mongo?
Well, it didn't cost us anything to tap to it, and like Joe mentioned, we're playing with all these different big data solutions. Database guys said, hey, can you put in Mongo? And we said, sure. So they're using it.
Another thing
didn't
it
cost
gave
us
us
anything.
was a point of flexibility. All right, so we're about to talk about what we're doing with Kafka and HDFS, and there were some speed bumps, let's say, along the way. And by putting in this Mongo capability, it gave us an alternate place to write data if we're having issues with the Kafka HDFS approach? It's a good question.
Are you sharding it all there?
So the question was, are we sharding to Mongo? And the answer is, depending on the use case, in certain instances, we are sharding. Okay? And so that is driven from the client tier, right? So they'll say, for my particular use case, we want to be able to shard this data, and then they will work with the Mongo team to determine what an appropriate shard key is, and then that flows through.
So from your perspective, it's just set and forget.
We very much want to consider it set and forget, right? Now that's not to say that there haven't been use cases that have emerged where they've come back to us and said, how would you? And then we're like, oh, that's a good one. We're not sure. And then we rally, the troops and we try to figure out a solution. So good question on sharding. Okay, so now we've got data flowing. The pipes have data flowing to the reservoir. We're filling the lake. We're eating up all that 2 petabytes. All right, now that vendor RDBMS you saw in the initial architecture was never our target. Nobody wants to support 10 relational databases that we've licensed from some vendor. And all roads should lead to Hadoop, right? Everything we want in the data lake, and we want to leverage Kafka, all right? We wanted to eliminate all of those local message brokers that you saw that were being deployed with every single container. So for some of our apps, we have 120, 130, 150 application containers, every single one of them with a local queue, which meant that on the Spring XD side, we needed a stream to read every single one of them. Operationally, that's a lot of streams to support. We wanted to get rid of that. We wanted to continue to evolve in the public cloud, or in the cloud, I shouldn't say public. And then we wanted to make sure that with some of the data, we implemented some data standards. Right? So we found that different apps were logging different data in different ways. And so we made some decisions around things like timestamps. We wanted a very particular format for the timestamp, and we wanted it all UTC based, so that we didn't have to deal with things like Eastern versus non-Eastern time, and all those everything UTC. All right, so we tested 3 patterns for how to get to HDFS from XD, okay? And we discarded 2 of them pretty quickly. And Jason's going to talk about that in a minute. So pattern 1 was that we put an XD container on the Hadoop edge nodes, and we used the file sync to write files. Because for batch ingestion, where they were dropping files on the edge nodes, there was an existing script process that was listening for files and then running an ingestion process to bring them to XD. And we thought, okay, great. We could just drop files on and use that same batch process to ingest those files into the lake. A second one we looked at was actually using the HDFS or HDFS dataset syncs that come with XD out of the box. Putting a container node on the Hadoop edge nodes and just writing directly into the lake as we receive data. So we'd open up a file, we'd write to it, the file would close, it would get registered, and then we'd start the next one. And then the third one was to use Kafka to write to Kafka topics. And then within our infrastructure, the data guy said, when you write to HDFS using Kafka, it's Kafka to Flume to Lake. We didn't have any control over that. They stipulated that's the architecture that they wanted.
So, knee-jerk reaction is, well, why not just use the HDFS sync? Sounds simple, sounds direct. But based on some of our architectural setup, it made it less than ideal. I mean, we'd like to use it. You can write Avro or Parquet formatted data directly. But the way that our lake is set up is you've got the lake itself, and then there are these edge nodes on the perimeter. And the name nodes, the HDFS name nodes themselves, aren't visible to anyone outside of an edge node. So if you've got an XD cluster out in the cloud, it can't find it. You can get around that by putting an XD container on the edge node, and then you can tell that to join your larger cluster. And when you assign that XD container a group, when it comes time to deploy your stream, you can pass some properties that say, all right, make sure you take any HDFS syncs and send them to the groups labeled edge node. So that'll put the module itself onto the edge node container. And then on that container, we've got it configured to use a Kerberos key tab so that it can authenticate with the name node, and we can actually write to the lake. There's a couple issues. Once the data is written to the lake and your file rolls over, when you define an HDFS stream, you can specify, all right, I want my file to roll over when it hits 10 gigabytes or whatever. When it hits that size and rolls over, we need that data to go through our dataset registry process. And all that is a REST call, but that would be new work on our part. All right, so we got to build something that watches it and configure all that. Not a huge deal, but it's a little extra work. The larger issue was now we've got these containers on premises, we've got these containers and the rest of the cluster out in the cloud, and we're going over a WAN, and it's partitioned like that. So that's less than ideal. And it makes it more difficult from a provisioning standpoint as well. We're provisioning these XD clusters programmatically, and it's a lot harder to say, all right, we're provisioning in this cloud environment, and by the way, we need something on-premise in this totally different environment. It was messy, so we didn't like that answer. What we went with was syncing to Kafka, and we got a couple benefits out of that. It decoupled the provisioning of the XD clusters, and then the data guys can scale their Kafka brokers independent of each other. Once the data lands on the Kafka topic, they can create a Flume job that will stream that data into the lake, and then they can use a Flume intercept process to trigger that REST call for each dataset instance. So the second Flume finishes a file, flips it over, it makes a call, it's registered, and now that data can be map reduced and we can actually use it. So we don't have to do the extra work. We're not dealing with the network partition anymore, and we can scale the Kafka side and the AWS or the cloud side independently of each other.
Yeah, and by the way, that note here, data scientists love us. That's a great thing to have, by the way. All right, so.
Can you explain why the data scientists loved it? Well, they don't use Kafka, right?
No, but because we've got these millions of records flowing through Kafka, and they can then become a Kafka topic subscriber, they can basically just hook off the data that we're ingesting into the lake for whatever they want to do with it, right? So we're giving them lots of places where they can get at data. Because in the past, they would go, could I pretty please have some data? And we would go, well, that's an IT project, it's got to be prioritized, it would take us da-da-da-da, because we're doing it all in the application tier code. Now the application tier is just like, I'm just going to send massive amounts of data out. And now we've got places where we can tap it, we can sync it to multiple sources, we can write it to Kafka. So they can get at it in process off the streams, out of a sink like Mongo, off a topic like Kafka, or they can wait for it to be registered into Hadoop, map reduced, and turned into something, let's say, more useful than the raw data sets, and they can hook it from there. So they got.
What do you mean by registered data?
It's part of our data registry process. Oh, sorry, repeat the question. He asked what we meant by registering the data. And that's just an internal process where we tag metadata to these file instances so it's more usable to us.
Yeah, and that registration is what then kicks off a bunch of MapReduce jobs to say, hey, I just got a new data set. Run the MapReduce jobs, bring that in, bring it into the larger fold of all the happy data that's like living in the lake. So that's what we meant. All right, so
those of you working with Kafka know that currently it is unsecured, and that's a problem for us. We need to ensure the security of our data while it's on the wire between our Spring XD cluster and the Kafka broker. And we solved for that by using STunnel. STunnel is an open source program. It ships with a lot of versions of Red Hat. And basically, you install STunnel on the XD containers that are going to be making the writes to the Kafka broker. You install STunnel on the Kafka brokers themselves, and what STunnel does is it provides SSL, TLS security for applications that don't have it natively. And now we've got our secure channel, and we can write to Kafka. So what it actually does is you've got this STunnel program running on your XD container, and it's got a corresponding configuration file. And in that file, you define your external brokers. So what you'll do is you'll define a localhost port that you will write data to, and then a corresponding external address that it'll write data to, and then you specify the PEM to use to ensure that security. So you've got this running on the XD container, you've got a corresponding configuration on the Kafka broker, and that's how it makes the connection. When you actually define a Kafka stream within XD, it'll look like you're streaming to localhost 9091, 9095, or whatever. So the second that data comes in, STunnel picks it up on that port that it's listening to, and it funnels it over to your target server.
Yeah, so it's a nice little interceptor pattern that allowed us to close one of the gaps we have with the current Kafka implementation. So some other things that we chose to do is because we didn't want to put STunnel and the STunnel configuration and that port mapping on every single container in our ecosystem, we wanted to target the Kafka workloads to particular containers. So within the servers.yaml file, the YML file, there's a place called XDE container groups where you can define group definitions. Right? So one of the group definitions we could have, for example, is Kafka out. Right? And that basically would be a definition of a group. Then when we spin up a container, right, we can actually pass into that container via the -- groups option, or there's also a way to do this with environment variables, that container has the attribute of being Kafka out. Right? So now this container is spin up and it knows I'm in the group Kafka out. Great. So what's the next step? Now when we build a stream and deploy it, we can tell that stream where we want it deployed. So here in the Spring, this, by the way, this is what you would do in the DSL for the Spring shell. Mm-hmm. So here we're creating a stream. The name is APPTC01 audit. The definition is JMS in this example, but it could be Rabbit or whatever. So it's a JMS source on a particular queue name going through a custom module, and then it's going to Kafka, to a particular name topic, and to a set of brokers. Now notice the brokers here are localhost 9195 and 9196. And that matches what we have in the S-tunnel configuration, where it is hijacking, let's say, ports 9195 and 9196. And anytime it sees activity on that port localhost, it's immediately turning around, encrypting it with the PEM file, and transmitting it to its corresponding endpoint on the Kafka server on port, in this case, 9193 on IP address 102035. Okay? Now when we deploy the stream, right, stream deploy, we can provide optional properties. So -- properties module.kafka.criteria equals groups.contain Kafka out. So what we've said is when you deploy this stream, the Kafka module should be put only on containers that have the Kafka out attribute. There's other things you can do, like, for example, set the module count. So if we had multiple containers in that group and we set the module count to 3, it would ensure that there was 3 copies of that Kafka module spread out across the group. Right? So we can get some resiliency that way.
I think that these things have to change with the new data flow.
Yeah. So the comment was these things will change with the new revision of Spring.
The Spring Cloud data flow.
Yeah. Yes. Yes. Yeah, a lot of these things will change.
Sorry, I didn't see. Is the Kafka module something custom you wrote, or is that included with the XP package?
That's,
So the question was, is the Kafka module something we wrote, or is it out of the box?
It's out of the box, yeah. We're just telling it to go to our custom group of server, the Kafka servers that have S-tunnel installed on them. So it's just a group deployment specification.
Other questions here on this? Yes, sir.
I understand that you're encrypting data when you're changing them, but is there any data that, you know, at the end of the day, besides in the cloud, that you have to encrypt it and store it encrypted because you deal with, you know, it's banking, you deal with personal
Right.
information?
Yeah, so if you're familiar with the banking industry, payment card industry, DSS, data security standards, there's a certain set of non-public sensitive data that needs to be encrypted both in transport and at rest. Yeah, so folks are going, yes, I'm familiar. So the way we handle that is at the front-end applications, we provide the mechanisms to ensure that they don't log that data, or if they do, they encrypt it using application layer encryption before it goes on the wire, and then it's just treated as an encrypted attribute all the way through. Because even in this pattern where we securely get it to Kafka, now on the Kafka topic, it's sitting there, available for anybody. Okay, so we've covered that, but we're not done yet. So now we're going to talk about what we're going to do on the client side. All right, so because we've spent all that effort building out this big, rich, fat pipe on the server side, we now have some opportunities to do some optimizations on the client side.
You didn't mention where you deploy the server-side part. Is it in the cloud or is it your?
Kafka's running in our on-premises data centers. XD is running in the cloud.
And then S-tunnel secures that connection between the two. Yep.
Why Kafka as opposed to Rabbit?
Why Kafka as opposed to Rabbit? That decision was driven by the data team. So their architecture, they said, we want Kafka, Flume, HDFS. And they said, that's our, let's use the term everyone's using, that's our microservice, right? Except it's more of a macro service. They said, that's the front door. And we said, okay, fine, we can deliver to the front door. All right, so now we've got this bigger pipe, we've got better back-end tools, we can push more data. So before we had been telling the operations folks, hey, look, the databases are getting really big, we're spending a lot of money expanding storage. Kind of put yourself on a data diet. Reduce the amount of data that you're collecting, which is kind of very counter to the message, which is collect lots of data and let's mine it. Once we got this mechanism and we could get away from that relational database and go to Hadoop, we could flip that and say, yeah, go at it. So now our focus was make it easy for the client to get lots of data out and do it in a way that wasn't complex spell. All right, so one of the things we want to do was migrate to a central Rabbit. So get rid of that local queue, which at the time is, by the way, an active MQ broker, and move to a remote Rabbit, because remote Rabbit supports SSL, secure transport, dead letter queues, and a lot of other really nice features. So we wanted to be able to reduce the number of streams we had to define, simplify resiliency and availability, thin the stack down, so that basically our target for this normal data flow would be Rabbit through whatever custom processors to Kafka via that S tunnel, at least until Kafka supports secure transport.
And with the old architecture where each application has a local queue, that means you need a stream for each one of those application containers. So by writing to a remote Rabbit, you reduce the number of streams that you have to define. It simplifies your stream architecture as well.
So what we did on our framework side was we wrote a new library, designed a new library, which we call Data Framework Service. And basically what that gives is via configuration in Spring Beans, the option for the client application to annotate their Java objects and annotate their methods, and then we handle all of the assembly and the transport of that data out to a configured set of streams. All right, we're using standard JSON libraries, in our case it's Jackson, so that we can use the Jackson annotations to control how business domain objects get serialized into JSON. And then we're using some of the Spring integration support. So for those of you that love UML, here's kind of a high-level view. So the idea was that now applications could have a pool of what we called stream emitters. And so a stream emitter was the client-side part that was emitting data out. Think of it like channels in Spring integration. And so via the stream emitter implementation, we could attach a transformer and what we call a stream message entry point. So from the application's perspective, it's the door out, but from Stream's perspective, it's the entry point. So we call it a stream message entry point. And so the key here was then providing a simple mechanism with these stream emitters to write data out to these streams. And so the idea was attach a context, which could be a static object that describes the source of the message. So it would be the name of the application, the data center it's in, the host, the IP, like whatever data that would say this message came from this place. And then pass in object ... right? So they could just list objects, and the stream emitter would dutifully take those objects, run them through a JSON serializer, apply standardization on fields like currencies and dates and numbers, and then we'd get this composite JSON object that had a context and each one of these domain objects. So now the application teams didn't have to do special work anymore. They could just focus on writing POJOs that describe their business object domain, right? And then they could just send those objects out and let the XD environment handle the filtering out of data or the conversion of data. So what we would get on the POJOs was the ability to use simple annotations, like @JSON property said when I write out the time, write it out as EVT_TS, event timestamp. Or for account IDs, to your question about PCI DSS, one approach is, hey, don't write the account ID out @JSON ignore. It won't get serialized, right? And the rest of the data will. Another thing we did on that same PCI front is this annotation @non-public information. And so what that annotation does when it gets built and proxied is it actually triggers an encryption. So we have an encryption algorithm that applies symmetric encryption directly in memory on the machine. And so it takes that value, encrypts it, and then hands it off to the stream as a value to send through. And so it's encrypted in memory of the application, and then from there on all the way down, it's completely protected the entire way. And then if somebody wants to get at that raw data, they need to come back to the application team and say, I'd like that raw data, and then they have to basically register themselves, get what the key is, so that they can then decrypt the data. And that way we can ensure that there's no inadvertent logging out of sensitive data. Okay? We also provide, just like we had before, the audited annotation, which would audit out the attributes of a class. And then this new annotation we create, add event stream, which would take that execution of that method, its parameters, its return types, and hand it off to a default configured emitter. And that would then in turn apply the transform, turn it into JSON, and send it to whatever the configured endpoint is. And because we had some interesting use cases around being able to want to send the data to different places, we said, well, we'll support having multiple emitters. So in this particular case, our event stream is annotated to support an event name, let's just say foo. So this is the event name. And we have a standard event stream that says when this method fires, I'm going to send it to the log event stream, which let's say might be going to a file output. And then I have a separate custom emitter, which is of type audit, right? And the audit one is going to the audit emitter, which is configured to use a durable RabbitMQ so that we can ensure when those messages go out, we don't lose any data, right? So the first emitter, we might go, you know what, we're just going to send this off to this HTTP endpoint maybe. And if we lose some data along the way, that's okay. But for the audit one, we want to make darn sure that we take the best path forward to ensure we don't lose any data. The other thing that we get with those transformers is the ability to support more than just JSON. Because it's an interface-based approach, if somebody said, hey, I really need to take that data and do XML, or I want to do CSV, or a pipe delimiter, or whatever it is that they want, we're like, yeah, no problem. Just write a custom transformer, build a new stream for it, and you can stream that data out using that transform.
I have a question.
Yep.
So you use the audited to a certain thing, and then you have JSON property to describe, okay, I want to log that information, right? So when do you use, audited versus the other one, or is
Yeah, that's right. So the question was, like, how do we determine which annotation to use, right? So the @audited annotation would be just capture this piece of data as a part of the serialization of this object and send it out, right? And so then, oh, I see what your question was. Like, how does that compare against the JSON annotations, right? Well, they can be additive, right? So this basically just flags that this particular piece of data needs to be sent over to the builder that builds the actual message. Event stream only applies to methods. All right, so this is what an example of the config might look like. So if we were to open up the config property file for one of these applications, in this case, they're configuring 2 streams. And so when the application bootstraps, Spring will go through and instantiate a couple of different beans. So the first bean will be an HTTP emitter, so it'll have an HTTP endpoint, and it will have a JSON transformer. So you can see that here. And then when that emitter is configured, it knows that it's going to that host and that port. In this case, you can see it's secure equals true, which means that we're applying HTTPS, which means that we have to have a local key store with a certificate and a remote key store with a certificate so we can handle the exchange of keys and the securing of that pipe. In the second case, we're using a connection factory and JSON transformation for the queuing. Yes, sir?
A couple slides back, you were given during your Spring initialization, were you manually having something basically scan through, look for components that were annotated with this event stream and audited, and insert a proxy or something, or were you having some listener hooked up to, Java-based configuration of when the bean was returned, searching for this sort of thing?
Right, so the question is,
Actually implemented putting in that layer.
yeah, so the question is, in a nutshell, how do we handle the Spring initialization and the handling of these, right? So we're using like AOP proxy enabled, right? And every application that's using our framework will component scan for our common library modules. And then those modules in themselves will then look for a Spring configuration class, an @configuration class. And then in that @configuration class, we are then reading down for properties off the file system or wherever they're sourcing their properties from. And then we use that to control the @bean annotated methods that basically build the beans up and put them in. So there's a bunch of work that's occurring when the application is bootstrapping to create these various stream emitters. And in our case, we're using, I took that slide out too.
Oh.
So I had a slide in here that showed some of the configuration. I removed it. But yeah, so that's what we're doing at Bootstrap, is we're basically instantiating all these things, reading these properties, and using prototype scope beans to instantiate each one of those beans.
Final question on that. did you have a tool that would detect when you have one of these beans with this annotation that would insert that prototype for you, or when in the config, when the bean is being instantiated, the client application writer have to create the proxy, do all that stuff to hook into your...
Yeah, no, I think this is all Spring magic, right? When you're using Spring AOP and you have AOP enabled in the application context, then it knows how to generate proxies, right? So if we were to look at the code behind these annotations, that's where you'd see kind of some of the work. But it's really, really thin and fairly easy to do. If you see us after the show, one of us probably has an example on our machines that we can show you. After the show. That sounds funny. Da, 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 da. All right, and so here's an example of what that composite JSON structure might look like, right? So we have that context object, which is saying, hey, what was the source IP, source app, server ID? And then like an event outcome might be one of the objects that they handed off to the stream emitter to log out. In this case, it's saying this particular event, let's say it was that payment transaction, it occurred at this exact time, and we're using a UTC-based time format. The disposition code, in our case, 1 means success, but there could be other disposition codes. For example, a policy failure, a failure on a business rule, or a timeout on a service might result in different disposition codes. This is what gave our operations folks the ability to look at this data and really understand what was happening from a customer's perspective when they were using our application.
So this is what we look like now. We started out with single app, single container, writing to a local queue with another co-deployed app, going simply to an RDBMS. Now, we've been able to simplify our architecture, so we're writing to remote RabbitMQs. No longer are there local queues on every single container. We've gone from vendor containers to Tomcat. Everything's open source. We now can get data out through RabbitMQ, through TCP, through HTTP. Once it's in Spring XD, we've got our custom processing. We're tapping to Splunk. We're syncing directly to Kafka. Once it's in Kafka, we've got other tools and applications that can read from that real time. The data side configures a Flume job that automatically streams that data into the database or into the lake and triggers a Flume intercept process that registers that data. And we can also tap it off to Elk Elasticsearch. So where we started and where we've arrived, we can now send our data where it should be the first time, transformed and filtered as we like, independently provisioned of each other, and the application doesn't care about the data transport.
Yeah. Now, obviously, we've glossed over a few things, like, for example, with the HTTP sources, you have to have a load balancer of some sort in front of that, and you have to be able to like configure the number of streams you have so that you have resiliency. But that's all just deployment optimization and tuning. So now, in addition to that, what we have is secure. One sec. It's secure, which means that from the application, we can use SSL or TLS, either to an HTTP or TCP sync or to Rabbit. We can configure Rabbit itself to use SSL for all of its transport, and we can use S-tunnel coming out of Kafka to the Kafka cluster. So what was your question?
I see that you're using both Elk and Splunk. Is there a political reason for that?
We started with Splunk. Oh, so the question was, we have both Elk and Splunk shown up there. Why? Like many things, it's evolutionary. We started off with Splunk. We started using it, and we saw tremendous value in the tool, so we kept building more on top of it. Meanwhile, data scientists and folks in enterprise data services are out there looking at other tools. For example, Elasticsearch, Logstash, Kibana, Elk Stack. And they're playing with that and trying to determine, well, how much value does that add? Does that make things easier? Does it make it harder? Is it a better choice? And so I naturally expect when we are looking at a universe of big data tooling that's like this, that over time we will naturally kind of matriculate to a state where we have a smaller set of tools that become our preferred choice. So will Splunk always be there? I don't know, maybe not. Perhaps it'll be just Elasticsearch and Kibana in the future.
But the tapping makes sending that data to any endpoint a low-cost operation from our perspective. So all these big data tools that they're playing with, sure, have at it. We can sync it to whatever they want.
Yep.
Is there a Elk sync in the XD already?
There's not. So what we think, there's a couple things, like with Logstash, you can read files. It also, I believe, can receive data on TCP. And so this particular one, we're in an innovation cycle right now trying to use a TCP sync to write to an ELK stack and see kind of how stable that is. Okay. All right, so let's show you some example dashboards. All right, so this first one is out of Tableau. All right, so in this case, Tableau is showing logins and call volumes. All right, and so here we're seeing success rates on login. Over here, we're seeing the number of attempts a customer has to make to use to log in. Now, this one's particularly interesting because the green line is first attempt, the lower line is fails, and the red line is more than one attempt, I think.
Mm-hmm.
Yeah. No, did not complete is red. Multiple attempts is blue. So this says a lot of customers get on the first try. Some take more than once, which would be me. I forget my password occasionally. But then there's a whole bunch of people that don't complete. So this is one of those little nuggets along the way. Like, well, what's going on here? Is it something in our login process that's not intuitive? Or are our password requirements maybe something that are just difficult for people to remember? So this is something that triggers us to go out and dig deeper. What's going on here? Because if this is something that dissatisfies customers, we want to know about it, we want to fix it. All right? We're also seeing a number of folks who called an agent related to their login. Right? So this gives us a sense of how our processes are impacting customers and how customers are reacting to those things. And so if we're seeing high failure rates and high call volumes, well, that's pretty indicative we have a problem that's impacting our call centers. And so if we can reduce the failure attempts, then we should see a corresponding reduction in calls to the call center, as an example. Here is a Splunk dashboard we've called Genesis. And so this shows a number of different important transactions within our mobile application. So we're seeing in here mobile logins, payments, transactions, rewards, and reward redemptions over, this is a 2-hour period. Now the thing that's really interesting about here is that this is a rolling 2-hour window that's updated faster than every 2 minutes. So data is constantly coming into Splunk and this dashboard is constantly being refreshed. Okay? And what this is showing is that we have a fairly high transaction volume, a fairly low transaction failure rate, but we also have this kind of predictive score. So I'm going to kind of show a blow up on that. So here you can see we've got visibility into these critical transactions. In this case, it's the account summary. So when you log onto the mobile app, we go and grab your account summary, bring a bunch of data about your accounts and display that. And so what this shows over this 2-hour window is that transaction volumes are more or less stable, a little bit of volatility, but slightly declining. And then we have this, what they call a slick score. It's sort of like a predictive score that tries to look at that last 2 hours and tries to make a determination about how likely it is that we might see some sort of a disruption going forward. All right? Now, how those guys are doing that, don't ask me because I don't know. There's some black magic there. But suffice to say that they have been able to find a way to tap this data, do some complex event processing, and do some things that are predictive and statistically accurate, which allows us to take proactive measures if we see something that doesn't look right. All right, so that's Splunk. Here's a, yeah?
Do you know what tools they're using for CEP?
I'm sorry?
Do you know what are the tools they're using for predictive analytics?
Do I know, the question was, do I know which tools they're using for predictive analytics? And I will apologize for not knowing exactly which tools that they used. I'm sorry. Yes, sir?
So the Tableau dashboard, what's the source that Tableau is connected to?
In this particular case, this goes back to those first slides we showed with the ETLs. So they are taking data out of relational databases and ETLing it into Teradata, or they're taking data from HDFS, ETLing it and putting it in Teradata and hooking Tableau up on top of Teradata. All right, but there's a lot of interest in an alternate that doesn't have that same pattern. All right, and this, the question we had earlier about, well, why Splunk and why Elasticsearch Kibana? I think we're looking at Kibana as another possibility here. And here's an example. We're going to have a couple screenshots of some Kibana dashboards. So this one shows a service disruption in process. Right? So everything is green on a couple apps, but in one place we see something is starting to go wrong. Right? And then we see how that creates a corresponding ripple effect, and then how it heals as we start to, within the data center, start to switch traffic over to healthy systems, and how we start to sever ones that aren't healthy and bring new ones up to take the load on, and how we heal. All right? So all of that data collection and these dashboards then give us the ability to predict potentially impending service issues. So on the left, you can see here that we had some bank transactions that started to see an unacceptably high error rate, 5 to 12% error rate. And we were seeing that type of error rate right prior to some form of disruption on those services. Right? We also saw on the right-hand side declining mobile transaction counts. So things start to go, and then all of a sudden, oh, something failed. One of the services broke. And so oftentimes, oftentimes on that journey to look at one thing or building a dashboard for another, we find a piece of gold along the way. So in this case, one of the things they found in the Kibana dashboard was that pass rates were decreasing for 2 applications while traffic was increasing in that data center. And so they said, well, will you see a pattern that looks like this? Right? You can see that down in this area. Right? That's indicative that something might be going on, and that can then trigger us to have network operations or other folks go out and look at the environment and try to make a determination about where we have some problems so that we can automatically fix it before it becomes disruption for customers. Okay, so there was a question?
Yeah, do you guys do any aggregated logging at statistics on your logs or whatnot?
So the question was, do we do aggregated logging? I'm going to ask more details. What do you mean?
For example, finding the error rates with the number of transactions that are coming through.
Oh, yeah. So there's a lot of aggregate reporting. So there's like all those data sets that are landing in Hadoop are getting map reduced out, and there's different map reduction processes that are looking at different things, right? And we produce internally a lot of different metrics that have some cool names like Cal and Chi. Like I like Chi personally. Customer Hassle Index, right? So if the Chi score is high, then everybody wants to know why, because we don't want our customers to be impeded in interacting with our bank and our services. We want every interaction to be something that's seamless, that works right the first time, and then just delights them every time. And that's the synthesis behind all this data capture. Okay. So 2 more slides, and then you're free. So we're going to talk very briefly about what we're doing with environment provisioning for XD. All right, so we are in the cloud for pre-production and looking very carefully at the cloud for production workloads as well. In some cases, we have some pilots in production cloud. So we need to be able to mass produce these XD systems. Right? And so the way we've done that is that we've written Chef and Terraform-based provisioning scripts. So we trigger those from our Jenkins dashboard. It used to be Hudson, we've now moved to Jenkins. And so we have these jobs. So the lower one, create XD parameters, gives the application DevOps team the ability to go in and specify the attributes for an XD ecosystem that they'd like to spin up. Right? And so we'll ask them for a number of parameters. I'll show you a screenshot. And then once they've created that parameter file, they have push button create stack. And that will then read those parameter files, take some authentication credentials, and then it will run a bunch of Chef scripts to lay down the XD environment. And so on the Jenkins side, we're specifying things like, tell me the number of containers you would like. Tell me the number of zookeepers. Tell me the number of admins, the number of RabbitMQ clusters, and then other things, right? So as you know, Spring in the 1X series at least requires a database for the job application database, right? So for us to be Postgres. So we asked them to give us the Postgres path to the Postgres instance, the schema name, et cetera, so that we can provide that in the provisioning process. So this process runs through and asks them everything that they need, right? What are the security groups? What are the subnets? You know, how do you want us to create your environment? And then once that parameters file is created, we run that, and then we get an environment. And on the right-hand side, you see a screenshot from a console that shows you the environment that we created. And so in this particular case, I actually can't read it on my screen. It's like Spring XD Digital Streaming Dev 10, and then the different components like RabbitMQ, Zookeeper, et cetera, all get created, and we can see that they're out there running in the cloud, right? So this gives us the ability in like typically less than 10 minutes.
Yeah.
We can create an entire stack, right, and then set it up. And then all they have to do at that point is then go in and start doing their stream definitions and stream deployments. All right, well, thank you very much for your attention and for your questions. We very much appreciate it. If anybody has any other questions, we have a few minutes to take those now. Yeah.
What tool or mechanism do you use to actually spin up that software? You said you create the configuration, but what actually does this spinning up of the components themselves?
Right. So the question was, what actually creates those components in the cloud?
Kind of like Docker or anything like that?
Yeah, we had looked at Docker. Right now we're using Chef, Terraform, and Knife to create the instances out in the AWS cloud, which is where our dev QA environments are.
Two-part question. First part, what is the sophistication of your dashboard builders?
What is this? Okay, so the first question is, what is the sophistication level of our dashboard builders?
Are they like technical data scientists that know like R?
Yes.
Are they more businessy kind of people?
We have a significant number of very talented application designers, developers, and data scientists. I heard a statistic a few years ago that I'm not sure if it's completely accurate, but that we had hired 50% of the PhD graduates for that year to CapitalOne as data scientists. I'm not sure if that's 100% accurate, but we have a lot of data scientists who are highly educated, highly capable data scientists. And so they're out there building these dashboards or working in partnership with the business to solicit requirements and then put dashboards together.
So your workflow then, if I'm, say, like a lawyer, non-technical person, I have to submit a rec to a technical data scientist in order to get a dashboard. Is that right?
So the question was if...
For me, as say a lawyer, a non-technical person, to access that data.
Okay, so the question was, can a non-technical person get access to that data? All right, and the answer is, it depends. Right? So within, for example, some of our Splunk instances, we open that up to, for example, let's say we have a card for a card division or bank division. We have Splunk instances, and we will open that up for anyone to go in and use that environment. Right? In other areas, though, because of the nature of the data, access to that data is more restricted. Right? So we are, like many companies, we are agile. So we have agile Scrum intake processes. And so in some cases, it's yes. You make your request to a team that's responsible for building those types of things, gets prioritized against other work gets done. In other cases, there's the Kafka topic. Stand up your own elk stack and start consuming the data off the Kafka topic.
So at that point, I need to understand how else that works.
Yeah.
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 So for ad hoc reporting, how do you manage that?
How do we manage ad hoc reporting?
Yeah.
Good question.
Something happens, I need data right now. Do I just grab my own data scientist team and they just kind of roll the punches as I throw them out?
Okay, so yeah, so the question was, if something happens right now, what do we do? Well, then we have a bunch of smoke jumpers, right? So we rally the troops and we bring the right resources to the party and we use all the tools in our inventory to try to solve the question, right? And so you get a different level of activity if there's some issue or impending issue that we're trying to triage versus, I just have an experiment I'd like to conduct and I'd like to get some data. Yes, sir?
So in that topic title from our session, we talked about CEP, but I haven't really heard anything about rules engines or in-memory data grids or anything like that that is normally part of the CEP conversation. Have you guys done that?
Yeah, so the question was... So I'll repeat the part of the question I want to repeat. So the question was in the title, we did talk about supercharging CEP, but we didn't really talk about how we're doing CEP. Yeah, and so that's correct. In this, we were really talking about what we're doing with Spring XD to enable CEP, but not really talking about CEP because it's not a big data conference, right? It's a pivotal Spring conference. However, there are a lot of things that are being done within CapitalOne to do CEP, but Jason and I don't work in that area, so we don't have all of the details around what it is. So sorry if there was something that you were expecting that we didn't quite hit on. Any other questions? All right, everyone. Well, that's our content. And so on behalf of CapitalOne and myself and Jason, thank you for attending. We appreciate your attention and your questions.
Thank you.